Hello, welcome. So today I will show you a TEG model, okay, that I have created. Okay, so when you want to use this, because this is a protected file, you can see here when you download this file, you have two. Let me make it bigger. Okay, two protected data. Okay, so I will not show you the source code, but unfortunately we cannot combine this together. So in order to simulate the model, you have to make sure that you open the MATLAB folder correctly. So for example, I put it in this location, okay, this address. You have to copy the address, okay, Control C, copy, okay, click it, okay, click it, Control copy, and then paste it here in the MATLAB. Okay, this is just to ensure that the MATLAB able to run it. Okay, run the coding. Okay, this is the coding, TEG and the datasheet. You have to make sure MATLAB are in this directory, so then you can run this. So if you run this, okay, you can see here, okay, I already make the sequence. Okay, so basically this is the model only. Okay, you need to only have the TEG array. This one is just an example. Okay, you can change it according to your design. Okay, so if I run this program, okay, so you can see here, this is basically like a data sheet. Okay, this is like a data sheet, and this one is the result. Okay, so okay, so you can see here QA, QB, and W. This one is the voltage parameter, and this one is the temperature. Okay, so if you don't know, QA is basically the energy. Okay, heat energy at the port A. Okay, you have when you have a TEG, you have two sides, right? Side A and side B. So QA is the heat energy that flowing. Okay, plus is goes into, okay, minus is out of. Okay, so make sure you know QA and QB is just a heat energy at the side A and side B, and W is the electrical energy. Okay, and the other thing you have to look is the voltage. Of course, this is the VTEG, okay, and ITEG, the voltage and current at the TEG. Okay, and VOC is actually the internal voltage. Okay, so this one is inside the internal. Okay, so maybe, okay, and this one is the temperature change from 25 degrees Celsius to 45, and then reduce. Okay, you can see here I show the sequence: heating, cooling, and generation. So basically this is heating, increase the temperature, and then cooling, reducing the temperature, and then generation. So generation is basically connected to the resistor. Okay, so okay, if you don't know what is VOC, you can look inside here, look under mass. Okay, so VOC is this one, the voltage. Okay, when it comes to TEG, you have resistance and voltage. So VOC is this one. Okay, VOC or V internal. Okay, and for the temperature, okay, you can see here, I set it to 25. When you do generation, it will try to go to the the fixed or surrounding temperature. Okay, so that is how you interpret it. This is the power, this is the voltage characteristic and current characteristic, this is the temperature. So you can see here, this is data sheet. Okay, so for this data sheet, it is tested for 0 degree different, 20 degree different, until 80 degree different. So you can see here, this is the power flow. Okay, you can see here, this is electrical power. Okay, this is QA, okay, at the side A, and this one is QB at the side B. Okay, so you can see here, this is the COP, coefficient of performance. Okay, when it comes to heating and cooling, we using TEG, you have to make sure that the performance is at this point. Okay, so you can see here at this point. So basically, when the temperature is 80 degree, okay, you have to use current, maybe this one. This is the optimum one, COP highest. You have to use the current around 4 ampere to ensure that it is cooling or heating at the optimum level. For example, if you have 20 degree, okay, for 20 degree, this is the optimum one. So you have to put the current is around 1.3 ampere. Okay, you can use higher current, it's okay, but it is not very efficient. Okay, so when you design the heating or cooling using TEG, make sure it is optimum. The higher the COP, the more optimum the system is. Okay, so next is the current. Okay, this is just basically obtain the high value here, the highest value, and then just transfer it. So the temperature different, for example, if you have temperature different around 40, okay, the optimum current is basically 2.5. This one is just extracted to here. Okay, so for example, if you have 80 degree, 60 degree different, okay, the current needs to be 3.48. Okay, so that is how for cooling and heating. Okay, so this datasheet actually automatically produce when you run this, it will just come out. Okay, and this one, if you use for generation, of course, this is the IV characteristic, and this is the PV characteristic. Okay, not PV photovoltaic. This is the power voltage characteristic. So you can see here, when you do generation, make sure your operation is at this location. Okay, this one, if temperature different is decreased, so you have to operate at this location. So that is how to interpret the TEG datasheet or characteristic model. Okay, so you can close this, but if you already close and you want to open it again, just open the mask and click OK. Okay, it should be come out. It's okay. Maybe just run it again. Let me run it. Okay, so it will come out again. Okay, so looks at the setting. Okay, this one is in. Okay, you don't have to look at the inside. This is just a model. For this one, the code you cannot look because I already encrypt it. Okay, so this is okay. You don't have to understand it. You just use it. Okay, so double click this, and you can see here there are multiple settings that you need to do. Okay, of course, the first one is the TEG setting in the module. Okay, when you buy the TEG datasheet, okay, let me show some example. Okay, you can search TEG datasheet and you can obtain some datasheet. Okay, for example, this one. Okay, the module characteristic is basically available online, so you can choose any. Okay, say okay, this one. So you can see here the AC resistance is around 1.7. Okay, you can set it here. Okay, thermal conductivity, this one is around 1.2, and sometimes seatback coefficient is not given. So how to determine the seatback coefficient? Okay, so try to look. Okay, usually not given, but another quick way to determine this is just look at the temperature difference. For example here, okay, you have to look at the current characteristic, current voltage characteristic. Let me find it first. Okay, for this one doesn't have. Let me check another. Okay, this one is much more better. You can see here you have a V over K. Okay, V over K is basically the seatback coefficient. Okay, so you can use this value in here. Okay, this is match ohm, is basically the internal resistance. Okay, so thermal conductance, I think this one. Okay, this one. Okay, you can obtain this from the datasheet. And then array is how basically you want to connect all the TEG. Okay, this is TEG, a small TEG. So you have to combine this together to make a visible. Okay, if you just use one, it's not not very visible, not very useful. Okay, not very useful. So you have to connect it together in series and parallel, so it become array. Okay, and then this is a sample time. This is just I suggest don't make it too big or don't make it too small. Okay, because if it is too small, you have to simulate a long time. If it is too big, you have to the result is not too accurate. Okay, so 50 I think is okay. 50 microsecond. This is the TEG itself, and then the storage. Okay, so storage means that, okay, when it comes to TEG, one side usually goes to the surrounding. Okay, and another side is connected to a material. Okay, something that is heating or heating up or cooling down. Okay, so you have to know what is the mass of the maybe I show you figure. Okay, so you can see here you have an object. Okay, and then you have a heat sink. So heat sink is basically the surrounding, so the temperature at the heat sink will kept constant. In theory, it will kept constant. Okay, so the object will be changing temperature or doesn't change depending on the object. Okay, for example, here you want the object to cool down or heat up. So this object needs to know the mass. Okay, this is how many kilogram is it. Okay, and then you need to know the specific heat capacity. Okay, specific heat capacity, you can just Google it. You see this constant. Okay, specific heat capacity. So for example, if you want to use water, okay, so specific heat capacity for water is 4,000. Okay, so you just put it here. Okay, how about oil, cooking oil? Okay, so for cooking oil, you can see here specific heat capacity, olive oil and everything. So make sure you be careful with the unit. This one is using kg Kelvin. Okay, so this is how you obtain the parameter of the storage, okay, or object. And then next is the temperature. Fixed temperature is basically the surrounding temperature. Okay, so if you look here, where is it? Okay, so what is the temperature of the surrounding? Because it will goes into the heatsink, and heatsink we try to ensure the temperature is fixed. Okay, and then the initial temperature of the TEG. So this object, what is the temperature of this object at the beginning? Okay, so usually for example, if the temperature change, okay, if you want to cool or heat this one, okay, we usually just fixed TEG means that the temperature will change. But if you put it yes, means that the temperature of the object is not changing. This one is usually the object you want to use. You want to extract the heat and create the power generation. So that one you have to change this one. So depending on your application. But if you don't, you want to cool down and heat up the object, you have to use no. Okay, this one is usually for generation, where you have a heat source. Okay, heat source, and you want to extract the heat. Okay, you use this one. Okay, that's it. This is just a detail, okay, of this. Okay, that's it for the setting. Okay, so try. You can try your simulation. You can try this. Okay. Okay, so good luck with your simulation. Oh yeah, before I forget, I just want to show you what is the simple simulation is all about. So you can see here, this is positive. Okay, it goes to two sides, either a current source or resistant. Okay, so you can see here heating, cooling and generation. So for the first one, you can see here it goes to the source. Okay, and for the source, the first one is positive current and then negative current. Okay, so basically when the positive current, okay, so this one is flip, this is OR, not So basically when this on, this is off. So during heating, you can see here, this is heating. This is heating. Okay, heating, your current just inject into the positive side, and then for cooling, you just goes the opposite way, the current, and then for the generation, you just connect the TEG into the resistor. Okay, so I think that's it. That is what is the TEG array is all about, the TEG array model.